Today, we will see in detail the rotation in classical mechanics. After getting some understanding about the rotation in classical mechanics, we will move on to rotation in quantum mechanics. Now, we will see the rotation in classical mechanics in a detailed manner. Just to go through my diagram, I have given x and y axis in blue color, which is the original axis. I am rotating this in counterclockwise direction by an angle of pi. So pi here pi. So I am rotating this by an angle pi. Uh, this new axis is x prime y prime. Original axis is x y. And here I like to highlight one important point that I have not drawn this to the scale. Now you apply the trigonometry relation. You see the first one, that is x1. X1 is this one, and x1 prime this one. That is adjacent side to opposite side for this angle pi. So which is equal to x1 over x1 prime is equal to cos pi, because it's adjacent side to a hypotenuse. So which says that x1 is equal to x1 prime cos pi. Then you come to next one, this side, minus x1. So minus x1, this is parallel to that, minus x1. This is minus x1, which is opposite side for this angle. And this is hypotenuse, see y1 prime. So minus x1 divided by y1 prime is sine pi, because this is opposite side to hypotenuse. So the x1 can be written as minus y1 as y1 prime sine pi. So because this I am keeping to the right hand side. Uh, then next you come to y1 to x1 prime. Y1 is this one. Then x1 prime. What is this? Y1 is parallel to this. That is opposite side for this angle, opposite side to adjacent side. So y1 divided by x1 prime. X1 prime is this one. X1 prime is this one. Hypotenuse. Y1 is this one, opposite side. So which is equal to sine pi. That means y1 is equal to x prime sine pi. Then you come to this one, y1. Where is y1? This is y1 is adjacent side for this angle, adjacent side to hypotenuse. This is y1 prime. So y1 divided by y1 prime is equal to cos pi. That is y1 is equal to y1 prime cos pi. Now you can you can represent these four equations in the form of matrix. You can see, of course, we are rotating along z-axis. So I am taking z-axis as 0, because there is no rotation except the diagonal element. Of course, I can make it by 2 by 2 matrix, but later on we are going to deal with the three-dimensional one. So I used 3 by 3 matrix. So z-axis also I have taken, but there is no rotation, no change in z-axis. We are rotating along the z-axis. Now you can see here, cos x1 is equal to uh, x1 prime. You multiply this row and this column. X1 prime cos pi, first term x1. Then minus y1 prime sine pi, the second term. Of course, third one is z. Z1, there is no change in z. Then you multiply second row, first column. So you will get these two things. That is x1 prime sine pi, and y1 prime cos pi. See, in some textbook or some lecture, you can see they should have noted this as minus, this as plus. There is nothing will change, except instead of rotating counterclockwise, if I rotate clockwise, then this will become plus, this will become minus. That is, imagine that I am rotating this red color axis to counterclockwise. Then y will become minus y because it goes to it. This axis will go to negative x-axis. That's all. It's a sign convention only. Nothing will change. So with this, we will move on further. So just now we have seen the rotational matrix along z direction, which I am representing as r z of pi. Pi is the rotation angle. So cos pi minus sin pi 0, sin pi cos pi 0, 0, 0, 1. If it is y-axis, then this y row, y column will become diagonal matrix. Here you will have one, other elements are 0. If it is x-axis, then this diagonal element is 1, all other, this is a x column, sorry, x row, x column. Other elements are 0 because we are rotating along x-axis. These three are the rotational matrix along x direction, y direction, and z direction respectively. Now we will take the rotational matrix along z direction as an example. So you know the rotational matrix along x-axis. Uh, Assume that we are making infinitesimally small rotation. That is, pi value is very small. That we are taking as epsilon, very small rotation, epsilon. You know the expansion of sin x is x minus x cube over 3 factorial plus x pi over 5 factorial. It will go on. So it alternate plus minus minus plus minus. Similarly, here also for cos x, you can have 1 minus x squared by 2 factorial plus x power 4 over 4 factorial minus. So here also alternate plus minus. So this is power series expansion. Now assume the pi is very small, epsilon. So rz epsilon, how you will write this? See, first term is cos pi. Since cos pi is epsilon is very small, you can take only the first two terms in the expansion, because since it's a very small, higher power will be ignored. So higher order terms will be ignored. So this cos x will become 1 minus from this expression 1 minus epsilon squared over pi 2, because 2 factorial is 2. You remove all other higher order terms. And when x is very small, sin x will become x. So that is when pi is epsilon is very small, sin epsilon is epsilon only. So which is equal to minus epsilon here. Because the epsilon is small, epsilon q is negligible in that way. So here sin pi, then it will be epsilon, and cos pi 1 minus epsilon squared over 2, and all other term will become 0. In similar manner, the rotational matrix for a very small rotation along x-axis, you will get 1, 0, 0, 1, 0, 0. Remaining thing, in the place of cos, you will get 1 minus epsilon squared by 2. In the case of sine, you will get epsilon. If it is minus sine, minus epsilon plus sine x and plus epsilon. Same is the case for rotational matrix along y direction. This is rotational matrix along y direction. See, this is y, y row, y column. Here, x row, x column. So we got all three rotational matrices for infinitesimally small rotation. Now you can carry out the matrix multiplication. Rx, Ry, that is Rx of epsilon, Ry of epsilon. This is for X matrix. X row, X column, first row, first column will be 1, 0, 0, 0, 0. If you multiply that with the Ry, see here, you will get this one. See here, you notice carefully, I have written only two component in red color. There is a meaning for it. Then you multiply Ry with Rx. Uh, Simple multiplication. Uh, that is the reason why I am not carrying out this multiplication. Only thing is I would like to highlight it during the multiplication. You will get here C for epsilon. So sometimes you may get epsilon cube and epsilon power 4. So you can ignore higher order epsilon because epsilon is very small. Then finally you will get this expression. This matrix and this matrix are exactly same except here epsilon squared and 0 replaced. So if you carry out the first rotation with y and rotation with x, first you are operating on y, rotation y, and next you are operating on x. Uh, which is not equal to first you are operating with x then y. There is a difference. This different actually physically we can explain, but however that is not my aim. You can see there is a change in it. So all other term will get cancelled if you subtract this and this. We are going to see. So if you subtract these two, that is Rx Ry minus Ry Rx, you will get that epsilon square term only because all other term will get cancelled. So you will get epsilon square minus epsilon square here. All other term will get cancelled. And we have seen that RZ matrix is this one. See, just to notice this diagonal element. This if you replace RZ matrix by RZ epsilon square, you replace epsilon by epsilon square, then this will become epsilon power 4, this will become epsilon power 4, this will become epsilon square. So that means epsilon is very small, epsilon power 4 you can ignore. So all these three diagonal element will become 1. This epsilon I am replacing by epsilon square, this epsilon minus epsilon square. Because rotational matrix, I am writing the rotational matrix for epsilon square. So Rx Ry minus Ry Rx is equal to Rz epsilon square minus 1. Rz epsilon square minus 1. So if you subtract the unit matrix, you will get back this one because all diagonal element will get cancelled. And I like to highlight that one important point. You can see we are going to see in quantum mechanics Lx Ly minus Ly Lx is equal to IH cross Lz. Similar thing we will see this. Here in quantum theory, we will talk in terms of computation. Here we will see in different way. I will explain why this operation, both operation is not equal. That is, first you are carrying out Ry, then Rx, which is not equal to first you are carrying out Rx, then Ry. We will see using a simple diagram now. Now I will explain the concept in a simple manner. I have a slab like this. Now I am rotating this slab by 90-degree along z-axis. So this will come like this. Now if I am doing the same again along x-axis by 90 degree. So this slab will look like this. Now you interchange the operation. This is my slab, original slab. First I am rotating 90-degree along x-axis. So this will become like this. Then I am rotating along the z-axis by 90-degree. Then it will come like this. You can clearly see the both are not equal. That is the reason why when you are doing rotation in classical mechanics, first with X matrix and Y matrix, then the result will be different from first you are doing with Y axis, then X axis. So Here we are not saying this is a commutation process. This is about the classical. In quantum mechanics, still we have some commutation problem also that we will see that in detail in my next class. Uh, that is rotation in quantum mechanics. Thank you very much for watching my video and supporting me continuously.